So I'll talk about what those mean in a little bit. But there are two basic models. He actually gave a few more, but there are two that are kind of important for you to know on the exam. And the first one is the integrate and fire model. These are all computational models of neurons. So this is not how neurons behave in the body, but this is how we think that they behave computationally, so we can do cool things in MATLAB and on the computer. So basically this one is pretty simple. You just put in some current, and it has a mean. That's what I bar means, but it fluctuates around the mean. And what you see is that the voltage V naught is the membrane potential, will slowly rise, and the model posits that it will rise until it hits a threshold. At that point, it'll spike, it'll set down to V reset, and then it'll continue increasing again until it hits the threshold again. So this is just a model of how neurons fire and how they respond to input. Now the hard part about this model is trying to correlate complex inputs with this current right here. But the spiking behavior is pretty easy in this case. It just increases until you hit a threshold, it spikes, and it goes back down to a reset voltage right here. And these are the dynamics. You covered this in SBE 1, so I won't cover that in too much detail. But it's just from the resistor capacitor model of the membrane. But the one that is kind of the focus on in feed-forward and recurrent networks is the firing rate model. This one is a little bit more abstract. This one is very tied to the biology of neurons, and this one is a little bit more abstract and computational. But essentially, you have a bunch of inputs represented by W right here. So the W's are the weights. You have a bunch of inputs that correspond to each weight, and you add them up, and then you put them through some nonlinear gain function, and then you get an output. So here's an example of certain gain functions. So over here, you have the logistic and sigmoid. Over here is a step function, and then this is the linear. A different version of this is used in perceptrons, which is to follow. But you can use different nonlinear gain functions if you want a different property in the neuron. But essentially, this is the main form of this type of model. Here are all of your inputs. Here is the weight. You add them all up, and there's a certain threshold. So you need to be above a certain level for the neuron to fire. And firing is a 1 in this case. So are there any questions on integrate and fire or the basics of the firing rate model? Yeah. So
is the threshold thing just the G? Is that like a function?
So G is the function. G is any one of these functions. And there could be other ones. H is a number. Okay. It's like 5 or like 0.5 or whatever. Okay. Yeah.
The firing is like a 1, but like the gain functions doesn't actually go to 1 immediately. So the Y value can be like between 0 and 1.
Yeah. That's why people normally use a step function or a sine function. Yeah, that's a good point.
And X is the input?
X, yeah, so X is all the inputs. W is the weight, so how much they affect the output. You add them all up, you subtract a threshold, you put that into a nonlinear gain function, and then you get the output. That's the gist of it. So pretty simple, but you can do pretty complicated things with this type of model. Cool. Okay, so I'll move on. There are two types of networks that Dr. Zhang talked about in his first 2 lectures. And the first one is a feed-forward network, and the second is a recurrent network. So a feed-forward network means that nothing goes back. Everything goes in one direction. Everything feeds forward in the network. Recurrent means things you have like loops and things kind of go back on themselves. They can connect to themselves. So these are a little bit more complicated. But perceptrons, multi-layer perceptrons, and optimal linear mapping all fall under feed forward. Things only go in one direction. Nothing goes back. And then Hopfield networks and mutual inhibition falls under recurrent networks. So that's kind of how I'm going to divide up my part of the review session is feed-forward versus recurrent networks. So moving on to feed-forward networks, like I mentioned, the nonlinear function over here is a sine function. So sine just means it's pretty intuitive. If it's positive, it's 1. If it's negative, it's -1. And same thing, you add everything, you multiply all inputs by their weights, add them all up, subtract a threshold, put it in the sine function. So that's how you get the output of this neuron in this case. This is supervised learning, so you do need to have some way of telling the neuron what is right and what is wrong for the update equation. Like I said, the nonlinear, so this should not be a step, this should be a sign function. Step would just mean that if it's not positive, it's 0. In this case, if it's not positive, it's -1. There's a threshold h and weights wi. And the way that you update the weights, so what you would do is you would put in an input and you would tell it what is right. You would see the output. If it's wrong, you update the weights and you do it again. And you keep doing that until you get the output that you want. So this is how you update the weights right here. The change in the ith weight, what you do is this is your learning rate, so this is how quickly you learn. And this is super important. If it's too small, then you learn at such a slow rate that it takes 1,000,000 tries for you to get the right output. If you learn too quickly, you may pass the right output. So you want to modulate this. Capital Y is the right output. And then lowercase y is the output that you got when you put it in this. And then xi is the input. So this is how you update your weights, and you would keep doing that until you're sufficiently close to the output that you want. And there actually is some intuition to this. So I'll go on the board. He mentioned an energy function, and this is something that's very common in machine learning. Is you have some function that you want to minimize. In this case, you want to minimize the energy of your model. And in this case, the energy is 1/2 y minus little y squared. So the way you minimize that is you say that delta wi is just some number. In this case, let's just say it's -k times the change, the change in energy with respect to the ith weight, because we're talking about the change in the ith weight. And so if you just do this out, it's -k. The 2 comes down, so it is y minus little y. The negative sign cancels this guy out. And then you have the change in y over the change in wi. And then this guy is just xi. So that's the exact same rate equation that we get here. So the way that you can imagine this equation right there is you have some parabola or some complex function, and what this does is it gets you to the minimum of that function. So that's what minimizing the energy means, and that's why you have this update equation right here. Does that make sense? Cool. Okay. So I'll move on. So now kind of moving forward, this is just one neuron, right? It has a bunch of inputs and there's one output. We can kind of expand this model a little bit. So there are two ways to expand it. This one is you have multiple input neurons, but you also have multiple output neurons. And this is where optimal linear mapping falls. So you don't have to know the details of how you came about this, but essentially the optimal weights are given by this equation right here. And it depends on whether you have more rows than columns or more columns than rows. More rows than columns would mean you have a bunch of inputs and less outputs. And more columns than rows means you have few inputs and you have a bunch of outputs. So this right here is just called the Moore-Penrose inverse. And if you do have a square matrix, this just falls into just the regular inverse. But this is just a way that you can kind of get something that resembles the inverse from a non-square matrix, because only square matrices are purely invertible. But that's optimal linear mapping. And then this one is, so in this case, you only have one layer of inputs and you have one layer of outputs. In this case, you kind of have hidden layers inside that allow you to do more complicated computations. So one of the biggest issues with linear perceptrons is they can't solve the XOR problem. So the XOR problem, this is how it looks. So what the linear perceptron does is it tries to draw a line that separates, in this case, the black from the white. But there's no line that you can draw that would do that in this case. But the way that you would solve that is using something like this. So I'm just going to kind of walk you guys through it. What the number inside the little bubble means is that's the threshold for that neuron. And the outputs are, if this neuron is on, this is what it outputs. So for example, if I put a 1 here and a 1 here, then this guy outputs a 1, and this guy outputs a 1 to this neuron. Right? This guy needs a 1.5 to be active. It's getting 2, so it's active. So then now this guy outputs a -2, but you get a 1 and a 1 here, and they cancel. So there's no output. Did that make sense to everyone? Okay, so now let's do 1 and 0. If I put in a 1 here, this guy's active, so he gets a 1, but he doesn't have a 1.5. He just has a 1 from this guy, so it's not active. And it gets a 1 here. It's more than 0.5, so it's on. So this network is only on if you have a 1 and a 0, or a 0 and a 1. A 0 and a 0 and a 1 and a 1 will not activate it, like I showed you guys here. So this is a hidden layer, and you can just keep stacking these on to do more and more complicated computations. Yeah. Are there any questions on expanding perceptrons to either multiple inputs and outputs or hidden layers? Yeah.
Can you explain how output unit again?
So over here. So yeah. So this guy behaves the same as this guy right here. He needs a 0.5 to be active. He gets a 1 and a 1 from each of these if they're active, and a -2 if he's active. So it's the same exact thing. The number inside the bubble is the threshold. You need to at least have that much input for you to be active. And then the number by the arrows are, if it's active, this is what it sends out. Yeah.
So you're saying the hidden layer helps deal with OR problems?
Or
So
just
this
more
is-
complicated
Okay.
computations.
Okay.
Yeah.
But we can't describe that mathematically? Is that what you mentioned?
It's-
Like you mentioned we can't find a line?
Yeah, so that was more with this right here. What this does is, if you have a bunch of data, it finds a line that separates the data out. So for example, I'm going to go on the board again. For example, if you had, like, let's say this is height of people, and this is weight of people, right? And you have a bunch of zeros over here, and you have x's over here. And in this case, let's just say that men tend to be fatter and taller, and then women tend to be skinnier and shorter. What this would do is it would find a line like this that separates men and women, if that makes sense. If the x's represent men,
Perceptron?
that's what a linear perceptron does, yeah.
Yeah, that's the linear, that's what you're describing on the left side.
Exactly.
But you can't do that mathematically on the right side.
You can't use this to draw a line here, because there's no way, there's no line here that separates out the black and the white. Are we all good on perceptrons? Okay, cool. So now I'll move on to recurrent networks. So the first type is just this simple example. This is more dynamics. And so this is mutual inhibition and excitation. You have two neurons, and this guy excites this guy inhibits this guy. And in this case, because we're working with recurrent networks, they do have self-loops, and there is a cycle that goes on here. It's not a feed-forward anymore. It's a little bit more complicated. But you should know how to get from this equation right here, or this graph right here, to these equations right here. So the assumption is that every neuron automatically inhibits itself. So if you turn it on, eventually it'll go back off. And that's what these terms right here represent. You have a negative sign because eventually you would want the neuron to kind of stop spiking. This right here is from the self loops. And G, again, is just a gain function. They put that in there just so you can expand the model to different things. And then these are the thresholds right here. So depending on the relative values of the weights and the thresholds, you can either get something like this that goes to a stable equilibrium right here, or you can get something that looks like this, which is more limit cycle. So things kind of oscillate and they spike and then they stop spiking and then they spike and they stop spiking. Yep.
So why don't you subtract, since like WEI is inhibitory, why don't you subtract that value away from the change?
It would just be a negative weight. Yeah. Yeah. So a positive weight would be excitatory. A negative weight would be inhibitory. Yeah.
The WEE term and the WII, why are they? If it loops in itself to make itself turn off, why is that also not negative, or is that just again?
No. So this is inherent in every neuron. This is just a model that we put in so that a neuron can activate itself also. Oh. So this is a neuron inhibiting itself, but if you don't want that, if you also want it to activate itself, you would just set this to 1 and these would cancel out. They're just a way that you can kind of mold these models to different properties. Cool, okay. So that's mutual inhibition excitation. Now we'll get into Hopfield networks. These are slightly more complicated recurrent networks. So in the assumptions of a Hopfield network is that everything is fully connected. So all neurons have the possibility of connecting to every other neuron. Neurons don't connect to themselves. So you don't see one connecting to one, but it's connected to everything else, right? 2 does not connect to 2, but it connects to everything else. So it's a fully connected network that has no self-loops, and it's also symmetric. Each memory is a stable state of the model, so I'll explain what that means in a little bit. You can store multiple memories, and you can, if n is the number of neurons that you have, you can store up to 14% of n. So that's how many memories that you can store. And then you can also retrieve memories from either partial inputs, or if you damage a bunch of neurons, you can still retrieve the memory. So you guys did this in your homework where you put in half of an image and you get the entire thing back, or you damage half of the neurons and you still get the entire thing back. But it's just a little fuzzy. So this is a model of the way that we would all store our memories. Yeah.
Sorry, is it 14% of something?
Of the number of neurons that you have. So in this case, we have 5 neurons. So whatever 14% of 5 is, it's like 0.7. That's how many you can store. So essentially one memory. Yeah.
So is this not them not being able to excite or inhibit themselves? That's specifically for Hopfield networks that are recurrent, or can these ones too inhibit themselves? So
this is a Hopfield network. Right. They cannot inhibit themselves. So there's no opportunity for a neuron to inhibit itself. Okay. They inhibit their neighbors, or they excite their neighbors, who can then inhibit themselves, if that makes sense. But I'll do an example to kind of make this a little bit more concrete. But before I do that, I just want to get some terminology out of the way. So you have n neurons in this network. In this case, n is 5. But you can have however many that you want. And each one has an index i. So I just tells you which neuron it is. The state of the neuron is si, little si. And the way that you get the state is you sum up all of its inputs by their weight. You add them all up and you put them into a sine function. So the state is either 1 or -1. A memory is just a vector of length n. So your memory has to be as large as the number of neurons that you have. And each value, again, is either 1 or -1. And then the way you initialize a memory is you set the value of each of those neurons to that value. And then you see how the network progresses. So for example, if I wanted to store 1, -1, 1, I would set my first neuron to 1, my second neuron to -1, and my third neuron to 1, if that makes sense. That's how I initialize the memory. And then the way that I store the memories is in the weights. So the weights contain all information about the memory. Capital S is the memory that you're trying to store. So remember, lowercase s is the outputs of the neurons. Capital S is the memories that you're trying to store. And this is how you would store them all up. Primes just indicate other memories. So now I'll do an example where I'll try to store a two memories in a 5 neuron network. So again, I'll do some board things. Sorry about my handwriting in advance. Okay. So the model that I'll work with is if you have 1, 2, 3, 4, and 5. A Hopfield network says that they're all connected to each other except for themselves. So the way I can represent that is just a double-headed arrow. 1 affects 2 and 2 affects 1. That's all that means. And because they're symmetric, I can use double-headed arrows. Same thing for this one, same thing for this one, this guy, and then I also have this, and then I think I'm seeing this one. Yeah, I think that covers all of them. But this is the way that my network is connected. And let's say I want to store, the ones that I want to store. So my S is 1, 1, 1, negative 1, negative 1. And my S prime is negative 1, negative 1, 1, negative 1, 1.
What is prime again?
Prime is that's just my second memory, if that makes sense. So essentially, I'm just trying to store these two vectors in my network. And the way I would do that is, again, what matters is the weight vector. So from here, we can see if I want the ijth term of my weight vector, I just multiply the ith term of my first memory with the jth term of my first memory, add it to the ith term of my second memory times the jth term of my second memory. And then you continue doing that for however many memories you want to store. So in this case, let's say, so first, because there's no self-connections, I'll set all the diagonals to 0. There's no self-connection, so that has to be true. So let's say I want my 1/2 term. Okay, so what I would do is I would multiply the first term in my S with the second term, so that's a 1, and I would add it to negative 1 times negative 1. So that's a 2 right here. Did that make sense to everyone? I want the first, like the 1, 2 term in my matrix. So I'd multiply the 1 term here by the 2 term here, add it to the 1 term here times the 2 term here. We all good? So I'll continue doing that. So now this is 1 and 3. 1 and 3, this is a 1, and this is a negative 1, so this is 0. Okay, and if you keep doing that over and over again, I won't bore you guys to death, but essentially you get 0, 2, 0, 0, negative 2. Then you get 2 because it's symmetric, 0, 0, negative 2, 0, 0, 0, 0, 0, negative 2, 0, 0, 0, negative 2, 0, and then negative 2, negative 2, 0, 0. And I want to show that this actually does store the memory that I want it to store. So let's multiply it by this first memory right here. And this is going to be some voodoo magic math that it's all going to work out that I actually get this memory that I stored in. So let's do this. So this times this plus this times this, you just do the terms. And so 2 times 1 and negative 2 times negative 1 is a 4. Remember, we put it in that sign right there. So 4 is positive. So in this case, we get a 1 here. You do this again. So 2 times 1, and then negative 2 times negative 1. This is a 1 again. Then you continue doing that. So right over here, this is a 1 again. Over here, this is a negative 1. And over here, this would be, sorry, negative 2. Yeah, and so then this would be a negative 1 also. So we get the memory that we put in back in our matrix. And so if you do this with the other one, you'll also get the same thing. So this stuff actually does work. The math is a little bit convoluted, and there are a lot of variables to keep track of. But if you just kind of break it down by that, you will see the memories that you put in. Yeah.
Did you say you can only store 14% the number of neurons? So at max 1, how can you store 250?
Yeah. So that's an empirical law. That's something that, it's about 14, and that's a little bit more prevalent at larger numbers. So if I had 1,000 neurons, I'm not going to do that math, but I would be able to store approximately 140. Yeah, it's an approximation.
Does the learning rule of SI times SJ, does it only apply to Hopfield recurrent network, or?
What do you mean?
So when you did fit4 network, we use different learning rules.
Right. That's a different learning rule. This is a one-shot learning rule. So if you put in your memories in that way, as I showed over here, you will get the memory out. There's no continuous updating. Exactly.
Okay.
Yeah.
Was S and S primes random like that?
Yeah, I could call them S and P or whatever.
No, sorry, the values.
Oh, yeah, I just completely came up with them randomly, yeah.
What do you do when you sum the weights times the memory state and you get 0?
I'm sorry?
What do you say the sign is when you get 0?
Um,
When you sum the weights?
that's a good question. I'm not too sure.
The sign function returns 0.
It returns 0, okay, yeah, so it returns 0 then. Good question. That's all the stuff that I have. Are there any other questions? We're all good with recurrent networks and feed-forward networks? Cool. Okay, so I can...
Sorry, real quick. So for Hopfield in this case, W is always 5 by 5, right? Because your input and output.
Yeah,
It has to be the same.
exactly,
Okay.
yeah. How does this work? Yes, perfect. No. Let me just play it. Takes a minute.
Okay, so I'm going to talk about the next two Zhang lectures. These are like way more chill than the other ones, and this should be the easiest part of his material. I doubt that you should get anything wrong.
Taking the easy way out is the TA who does the easy way.
It was all that was left. The first lecture here is about place cells and a little bit of stuff about memory. There's a lot of just like random interesting information in here that I don't think he's going to include in any type of question. So let's see, like in the beginning, he was talking about memory loss, and he talked about this guy named Henry Molaison, or HM, who like back in the 20th century, he had to get his entire hippocampus removed, like both lobes, for some reason because of like seizures or something. It was a surgery. And what happened to him was that he was actually unable to form any new memories whatsoever. So all of his long-term memory was still maintained because basically the way your brain works is it has your working memory or your short-term memory in your hippocampus, and then eventually it transfers those into long-term memories that go into like your frontal cortex and other places. But so he had all those still, but he was unable to form any new memories. So he would forget everything like every 30 seconds. Similar to these movies, he mentioned both 50 First Dates and Memento. If you're going to watch one of them, definitely watch Memento because it has more than double the Rotten Tomatoes score, and I can vouch that it's a much better movie. So it doesn't really tie into the lecture that well. The next one was much more about memory. So the next thing he went into was the different types of place cells in the brain. So in your hippocampus and other areas related to the hippocampus, there's a lot of different types of neurons that specifically encode your location in the world. There are 3 different types: the head direction cell, the grid cell, and the place cell, and they do slightly different things. And they all have world-centered coordinates, meaning they have your body or your orientation are in relation to the landscape around you. And they use 2 different methods to do this. They use landmarks that are around you in the world. And it's not exactly visual. We'll go over it in a little bit. And then the second way they do it is by using something called path integration. So your brain actually keeps track of what you're doing as you're moving around, like which direction you're moving and how far, how many steps you're taking, so that like even if we turn the lights off in this room and you move around, you'll still know like which part of the room you're in. And then so this is an example of the head direction cell. So as you can see, there's a cell in your brain that has a specific tuning curve for whatever direction you're pointing in. So there's one that likes this particular angle, one that likes that particular angle. So this is a tuning curve example. So this one really likes 0 degrees, whatever they define as that, and it makes a really steep Gaussian around that. And then, so for example, this mouse, every time he's looking north, let's say, this particular neuron would fire, but every time he turns another direction, it wouldn't until he turns back and he's looking north again. And one more minor point is that the spatial memory is formatted more of as a continuous attractor network, because you want to be able to have your brain modeling all of the different places you could be, which is different than the Hopfield network, for example, which is a discrete attractor network. So this is another slide showing those head direction cells. As you can see, there's many different head direction cells with all kinds of different tuning curves, so that each one of them likes a different spot, but overall there's so many of them that they cover the entire angle that you could be looking at, all 360 degrees. And this is an example of an experiment where there's a landmark on the right side of the little circular chamber that the mice are in. So whenever they're looking 90 degrees to the left of the landmark, their head direction cells fire. And what happens is that even if you, say you rotated this landmark 90 degrees to the right, their head direction cell would also rotate along with the landmark because it's tied to that landmark. So if this podium is right here and I'm looking ahead and one of my neurons is firing, if I move it, say behind me, that head direction cell is not going to fire anymore until I turn 90 degrees to match where the landmark moved. So that's how it's tied to landmarks. That's the first method that they use to compute it. And then the second one is this path integration. So that's what I was talking about, where like even if we turn the lights off in this room, my head direction cell will still be firing when I'm pointing straight ahead because my brain still knows that this podium is right next to me. Any questions about this?
But for a specific time, not always, right?
Huh?
You will not do this for all the time. After a specific time period, this will vanish.
Oh yeah, it depends. It's like constantly evolving. Every time I guess you go into a new room, your brain probably identifies new landmarks to use. Another question?
The rotation thing, is that like, do they rotate it while the mice are in there, or do they like pick it up and then rotate it? Like, does it matter?
I think it's like a continuous thing. So if I rotate this a slight degree, it should go along with it in real time. And then if I rotate it more, it would go another distance along the way. So it should be a continuous thing. So the second type of cells are grid cells. So these ones are like, you can imagine as like tiles in the room. If you have black and white tiles on the floor, there are particular cells in your brain that like the black tiles. Every time you step on a black tile, those cells start to fire. And every time you step on a white tile, the other types of cells would start to fire. And that's what you see here. So you see these like evenly spaced out dots on the surface there. And those are different neurons firing at those different points. And another point is that they make a sort of hexagonal pattern, meaning that each one of them has 6 like neighbors spaced out at 60 degrees. That's just like the general pattern they like to follow. And this is sort of 3 different grid cells laid on top of each other. So you can see there's green, red, and blue, and they all have a different, slightly shifted orientation. So once again, you have so many different ones that it covers the entire area. Another thing about head direction cells, and actually let's talk about place cells first. Another thing, this is actually probably the most simple one, are place cells. So place cells are the third type, and that's just like if I'm in that corner of the room, one of my neurons is going to fire, and if I'm the other one is going to fire. Like each neuron as a place cell has a specific location that it prefers. And so tying that back into head direction cells, the place cells and head direction cells are actually coupled together. So if down here, these are the tuning curves of your head direction cells. So in the first two trials, the head direction cell likes this up into the right direction here, and your place cell seems to like the right side of the chamber. And then if you disorient the mouse by like spinning it around a lot so that its head direction cell gets confused, now it likes the downward direction. So it's shifted about almost 180 degrees to the clockwise direction. And you'll notice that this place cell originally liked this rightward direction, but now it's also shifted about 180 degrees around to more of the leftward section. So the head direction cells and the place cells are tightly coupled together, and whenever one of their orientations gets shifted, the other one likes to move along with it. Any questions? Okay. Another point. Oh yeah.
Sorry, I have a question about the grid cells.
Mm-hmm.
So what do the grid cells exactly encode for besides for like different colors on the floor?
I guess it's really difficult to understand like what exactly they would be helping out with. I guess it's just like one more form of information that you could be using in addition to having just the place and your direction in order to help your brain compute like maybe what the best path is to take or where you are in the world.
Thank you.
Mm-hmm. And then one more note about the grid cells is that they have different spatial scales. So some of them are very fine-tuned to like very specific spots. So every time you take another step, maybe that is a different grid cell firing. Whereas some of them have very large and could even be like super big grids. So say one grid cell likes Decker quad, and when you're on Decker quad, it fires. And then if you go over it by Mud Hall, the grid cell also fires, but not in between, if that makes sense. So it can have varying spatial scales. And about head direction cells, he described it as a continuous ring attractor, meaning that you can imagine all of these different states in a circle, and as your head turns, the activity moves from one neuron to the next, and it just rotates around this ring of neurons. And if we use that example of the ring attractor, we can start to think about the dynamics of it and what would happen if you actually tried to like model this. So if we think of it as a symmetric center surround connection where a neuron in the ring activates neurons around it, but actually represses neurons that are farther away. So this neuron X would activate these ones nearby equally on both sides, and it would also repress the ones farther away equally on both sides. Then what you get is if you had a starting stable state like this, and this was like the strongest part of it, over time it would just evolve straight across if this depth axis is time, and it would evolve so that the activity would eventually center to that particular spot. And a different initial condition would result in a different stable state. So if this was if you had another initial condition where this was the strongest activity initially, then it would evolve so that the bump would be over here. But you'll notice that the bump in this case just stays in the same spot and it doesn't rotate around the ring at all. Because the ring, if we cut it and laid it out as a line, it would go from 0 to 360 like this. So that's what they did here. And the mutual excitement in this ring attractor is what ensures that you can remember your spatial location even when you're in darkness or if the landmark's been removed or things like that. Because this neuron is exciting the ones around it, and then the ones around it are in turn exciting it back. So it's sort of like a positive feedback loop that's sustaining itself. But on the contrary, yeah.
I had a question about the last slide.
Sure.
Before that one. Yeah, what is What is this? Can you explain that?
Basically, one theory is that the place cells, or not the place cells, the head direction cells, right? Like they care about your angle that your head is looking at. So it just goes around 360 degrees. So one theory is that you can think of the neurons like abstractly as being connected in a ring network together, meaning that they just go around 360 degrees. So the neuron that likes 0 degrees is connected directly to the one next to it.
So it's not like it's like actually like this in our brain. It's just like an idea.
I'm pretty sure it's just abstract. Anybody have any feedback on that? He didn't really specify in class. This is really like abstract level stuff.
Okay.
And this means that since the ones at a certain angle are connected most strongly and excite the ones right next to them, that's why they have this local sort of effect, if that makes sense. Yeah.
So is the head direction input to this system?
The input?
Yeah. So like in the next slide,
Mm-hmm.
it says external input. So what's the external input for this ring attractor system?
Down here, I guess the external input would be the initial direction that your head is pointed at, if that makes sense. So like, I guess in this case, the initial state was at like 90 degrees. So your head was pointed this way and there was no activity initially because maybe you just turned that direction. But over a couple of minutes, if you look that direction, the activity would slowly grow and grow because of this sustained network. Even if you were in a dark room just looking at a wall, like it would eventually sustain itself and keep growing. Any other questions? Yeah.
Question, like, so would it be, even though like you can kind of like remember where you are in the dark, if you spin yourself like around, right, then like basically your ring attractor wouldn't like know where itself is.
Right. I guess it kind of makes sense. It can just get disoriented. Like in that example before, we were talking about the coupling. If you spin the mouse around enough times, it can get its ring attractor messed up. Like I think in class he gave like sort of a little anecdotal example of like, oh, you know, if you're walking around the woods, you can get lost. But say that you're supposed to go north to like get back to the road or whatever out of the woods. And if you think north is that direction, you still, even if it's the wrong north, you still like know that like to the left of you should be west and behind you should be south. So those directions always turn with you. Even if you get disoriented, your head direction and your place cells are still coupled together. But yeah, they're not a perfect system. It is possible for them to get disoriented, and it's not permanent. They're constantly evolving as you go into new environments, new rooms, and things like that. So if we keep going along with this abstract ring attractor network thing, and we have this, if we instead of having a symmetrical thing, so if you look at this neuron, you can see that it equally stimulates this neuron as it does this. So to the left and right, same. But what you could have instead is this asymmetric type of excitation where this neuron excites the ones to the right of it a lot more than the ones to the left of it. And if you think about them as tied together in a ring and you have this sustaining activity, if it's exciting the ones to the right of it a lot more, those ones are going to get stronger. And then the activity, the main locus of activity should move a little bit to the right if you went like a time step ahead. And then as you keep going along, it should keep moving along to the right. And that's exactly what we see here. If you start off at t equals 0 with an initial activity bump here, it would excite these neurons a lot more. So if this was the initial locus of activity, these ones would get really excited, and then it would move over here, and then and so on. It would get excited to the right of that and keep moving to the right. And as you can see here, as it evolves over time, the activity bump is going to rotate around the circle in what we call a traveling wave activity. So these are just like two different very abstract ways of thinking about head direction cells. And I guess we can assume that maybe there's both types of these systems in the brain depending on what your hippocampus needs to compute for you as far as spatial location. Any other questions about this? So we propose the question in class then, like you have these place cells and stuff, and you have them for this entire room, but what happens when you leave the room or if you run off the map? Like your brain only has a certain number of neurons. It can't encode every possible location in the world, right? So that's what kind of this diagram is showing, like what actually happens in the mouse's brain when it leaves the room. And the idea that they came up with, this is just like a theory, I don't think it's been proven or anything, but if you imagine the room as a square, right? What you could do is actually fold this together so that it goes end to end, and then you could connect, so that would make like an open cylinder, and then if you connected the ends of the cylinder, it would create this donut or torus shape, such that as you left the room, the torus would actually rotate inward, such that your sort of spatial location in the world would constantly be rotating. It sounds really weird, but on this slide, I have some cool animated GIFs to show you how this works. It's really hard to imagine without looking at these animations. So this is what I was talking about. It folded the room into a cylinder, then it connected the ends to form the donut shape, and I guess it stopped going. And then once you have that torus shape, it can rotate in on itself around and around, like eternally, if that makes sense. It's really abstract, and he didn't go into any more detail than this, but this is just like a really abstract way to think of it. I'm sure there's got to be a question about this.
What do we need to know? Like, what do we do?
I don't think you're going to get a question.
And say internal, external, infinite,
If he asked you like,
Whoa.
the only possible question I could see on this is if he was like, okay, so we have this, we have these different place cells, and say this place cell fires when you're on the edge of the room. What happens when you step outside of the room? Well, you could say that, well, in your brain, the space that you're in isn't actually represented as a square. It's actually represented as a 3D torus shape, such that when you leave the room, it just rotates around and like refreshes it, kind of. There's no better way to explain this. I'm doing the best I can. Yeah.
It's like a 2D plane, so it's a torus.
Yeah.
So how do you have your place cells like up and down?
Up in in 3D? Oh, I don't think he didn't go into like human 3D place cells. I don't know if we actually have them. We must have something. But the next slide. So he went into bats, and bats have a 3D place cell. So with people, he only talked about like 2D if you're on like a surface, but bats have like this 3D arrangement where there's one cell that likes the top right corner of the room, and then when the bat flies to the bottom of the room, there's another cell that likes that particular region. Yeah.
So you said it was like rotating towards practice?
Yeah.
Is that like, does it rotate slower like while you're in the room, and then when you leave it refreshes, or is it like, how does that?
I guess if you're in the room and the torus has a certain like radius, like a donut radius, if you haven't exceeded that radius, then I would assume it doesn't rotate until you actually like leave the space you're in. But honestly, I don't think anyone knows the answer to this. This is like a total abstraction. Like obviously nobody's figured this out yet. They're still doing like experiments with mice, like connecting, wires into their brain. So I think that's the farthest we've got. He had a lot of videos in the lecture. So if you want to see more experimental stuff, you should take a look at those. They're pretty cool. Any final questions on this torus craziness? Okay. Moving ahead. So the next thing, these are just some like random tidbits he threw in at the end. So like I was saying, bats have 3D place cells instead of 2D because they have to fly around. Another thing he talked about was Jennifer Aniston cells. So in addition to having cells for particular places in the world, your hippocampus also has specific cells for individual people and objects, which is really weird. So like these are like, I guess, post-stimulus time histograms from an individual neuron in the hippocampus, and as you can see, when they showed a face of Jennifer Aniston or like different pictures of her, it went off for her, which is weird. And then what he also mentioned is when they showed similar pictures of like a woman who looked similar but wasn't Jennifer Aniston or was even wearing similar clothes, the neuron didn't go off. So, and it's not just, they were just using this as like one example. There was also like, he used an example of like the Sydney Opera House. When they showed people pictures of the Sydney Opera House, there was another neuron that went off. It beats me how they figured this out, like how they found that exact neuron. I guess they just showed this person like...
It's not the same one in different people, right?
No, it must be, yeah.
This is just one example.
And as he said, yeah, like, and all of us must have different cells in our hippocampus based off our own experiences. Like if you were from another country and you didn't know about Jennifer Aniston, you obviously don't have that cell. Or when you're born, you probably have none of these cells. But then over time, as you learn new things, apparently you get weird individual cells that have these connections. So he mentioned there are two different theories about this. One theory is something called grandmother cells, which is basically just the idea that like each one of these neurons is really actually individually connected to like a particular person or a particular thing. So you probably have a cell that goes off every time you see your grandmother. But the second theory he said was like population based, which he said he would talk about in the next lecture, but he never actually did. And I think what he meant there is like, it's possible, and I feel like it might be more likely that this cell doesn't actually prefer Jennifer Aniston. Maybe it just prefers like the particular arrangements or colors or whatever that's going on in the image itself, like qualities of the image as opposed to that particular person. But really, who knows? And I don't think you'll get a question on that one. So, but now we can actually do a quick little exam question here. So if you have, this is a ring attractor network type example, or a recurrent network. So if you have 30 units that are, connected as a ring, so there's 30 on the x-axis, 30 on the y-axis, because they're all connected to one another. The weight matrix, which is shown here, specifies the strength of connections from unit I to unit J, so just any two neurons. So there's 30 and 30, so there's 900 total connections. And the black activity is low weight, and the white activity is high weight, meaning they're very strongly connected. These weight matrices are shown. So there's two different examples. This one, as you can see here, has the white stripe directly down the diagonal, meaning that the neurons are most strongly connected to themselves. So neuron 1 has this best connection to itself. Neuron 5 and neuron 30, for example, all are best connected to themselves. And then this over here is the same sort of layout, but as you can see, it's shifted a little bit down and to the left. And since this goes from 0 to 30 and 0 to 30, you can think about like if it shifts along this diagonal, it's actually just rotating around the ring. So this stripe of activity has rotated a little bit. Then it's here. So now neuron 1 is not actually best connected to itself. It's best connected to like neuron 6. So the neurons are best connected to neurons that are a little bit to the right of them instead of to the same location. So we can think of this as more of the symmetrical ring attractor network, and this one is more of the asymmetrical ring attractor network because the activity is moving in one direction. So it wants us to answer the following questions. So there's you could pick A, B, both, or none. So this is A, B, and the answer could be both or none. So I guess we put the answers up already. Oops. So which weight patterns are symmetric? That is where Wij equals Wji. I mean, I gave that away before. If you think about it, the stripe is going right down the diagonal, so they're best connected to themselves. And then like if you look at the connection of neuron 15 to neuron 5, and neuron 5 to 15 here, like both directions, then that's the same color as that, if that makes sense. Like on either side of it, it's symmetrical. So A is the only one that has the symmetrical connections, because B, if you go right down the diagonal, it's slightly shifted. And what this means, as we talked about before, which of the weight patterns may generate a traveling wave of activity? When we were talking about ring attractor networks originally, the only ones that can generate the traveling wave are the asymmetrical ones. So only B can do that because it's asymmetrical. And then which weight patterns are shift invariant? That is, the weight between two units depends only on the relative position but not their absolute positions on the ring. Well, both of them have this shape where it's not like, it's the same on both sides, it's just that this one is slightly shifted. So they're actually both shift invariant. Like this connection, if you go up and to the right, you get the same thing as if you're here and you go up and to the right, for example. Questions about this example?
The shift invariant thing, like, but if A to B is shifted, how is it shift invariant? What's the difference between that shifted terms?
It means like, so say we have the connection between 15 and 15, so that's right in the middle stripe, and then the connection between 15 and 10, I guess, which would be over here. So there's there and there's there. So we have the white bright white there and complete blackness there. And then if you shift the whole system a little bit, which is what happens when you go from A to B, we have 15 and 10 connected. That's still in the white stripe area there. And if we do 10 and 15 connection, it's still in this blackness over here. What it means is that, as you can see, the whole system has shifted together so that only the relative location matters, because none of the pixels got like mixed up. They all moved as one unit. The ring just turned like 90 degrees, if that makes sense. Yeah.
What would it look like if you had a non-shift invariant system?
I think that would mean like if you shifted this, then it would somehow distort the shape of this. So it would no longer be two white stripes. Maybe if you shift it, something happens such that another white stripe appears or something, and then in that case it wouldn't be shift invariant. But I think that would be a pretty weird example. It should be shift invariant, I believe. Yeah.
It shouldn't be like just like not diagonally straight down, like an angle kind of. That's not 45 degrees.
Oh yeah. Wait.
Shift invariant.
Yeah. Right, because in this case, it's the stripe of activity is directly perpendicular to the direction that the ring rotates. But if the activity stripe was, say, horizontal, and then you shifted it, when you rotate the ring, it's really moving it from the top right to the bottom left corner, then when you move it, it won't be shift invariant because the weights between them will have changed. That's a good point. Yeah, I think that would work.
So it's not shift invariant if the movement of the band of activity is not perpendicular to the band.
Don't quote me on that.
Okay.
But like, if you work it out, like think about if you rotated the ring, what direction would that move it? And it would move it across diagonally like this. And in this case, we have a activity band that matches, that seems to like move along with that. Okay. Let's move on from this stuff. Oh yeah, one more.
And like, so we have the diagram is supposed to represent a ring, right?
Mm-hmm.
So what does shift invariant mean in terms of the ring? Like what's actually happening? Because shift invariant means like if you rotate the ring, I don't know.
Let's go back to the original ring attractors, maybe. I don't know. Anybody else? Luke? Anybody have an idea on this? I'm not really sure.
It means that you have the same response regardless.
Yeah, wait a
which
second.
neuron you have. So you have that same type of Gaussian regardless of which neuron it is. That's what it means when it says shift invariant. So like you have the same response for a given neuron. But then if you move to a different neuron, like 10 neurons down the line, it has the same exact response, but it doesn't excite the same neurons as the other one. Does that make sense?
Yeah, that makes sense.
Yeah, that's a good way to explain it. Yeah. Where? In these, or?
Where you show the picture of the mouse head one way.
Oh yeah. Let me see.
And then it's kind of an angle. So something like this where you get the same response, just in a different location.
Yeah, same shape. So even though the mouse turned its head, only the activity bump has moved. The shape of the activity bump hasn't changed. I guess that might be the best way to think of it. Did you have a question still? Same idea. Okay. Yeah.
Now I'm hungry.
Talking about donuts.
The breakfast biscuits.
The next thing is lecture 33, which was about learning and memory. So he mentioned that there's 3 different abstract ways that the brain can store information. You can have sustained activity in a single neuron, which is more like LTP. You can have sustained activity in a network of neurons, which is the ring attractors we were just talking about, and many other examples. Or you could have a change in synaptic connections, which also has to do with like Hebbian learning. So once again, abstractly, you can think of memories as stable states. So each of these points here would be an attractor, and these lines are the boundaries between them. So if you have a memory that's somehow in between states, it'll gravitate towards one of them. And this type of memory requires many neurons, and the synaptic weights are constant if you think about this abstractly in this case. I wouldn't worry too much about this. Moving forward, we had a lot of concrete examples. So this is sort of like LTP. A single neuron can have many stable states. It's not just like a binary thing like ones and zeros. You could have, so what they did in this experiment, they had a neuron with initially no firing rate. They applied a high frequency stimulus to it, and then they noticed that the firing rate had increased a little bit, and they applied the same tetanus. The firing rate went up, 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 and up each time they applied the tetanus, and vice versa. If they applied a hyperpolarizing tetanus, what they found was that the firing rate activity would actually step down again. So the neuron can have many different discrete stable states just by different stimulating it. And this was observed in the entorhinal cortex. And then, so that's an example of a single neuron storing a memory. Another example of how a single neuron can store a memory. In this example, they applied this tetanus to the neuron, and they noticed that the response, these are trials on the y-axis. So this is a spike train, this is another one, etc. So what they noticed is that every time they applied this tetanus, they get these kind of staggered responses. It's not the same thing every time, and it keeps changing. But when they gave it a simulated random bombardment, which is similar to what a real neuron would get through its synapses from other neurons, you can notice that the current looks very random here, but the output they get is actually really similar every single time. So this is a sort of weird behavior. We didn't really tie this into the rest of the class material, but the best way I can think of it is that neurons we think of them as stochastic all the time, but sometimes they can actually be not so random and can have very specific responses. And this neuron seems to sort of, it's actually remembering this input current, which is really weird because it seems so random, and the neuron is just a simple cell that takes in inputs and gives out outputs, and yet somehow through calcium channels or something, it's remembering every specific input and giving the same output 25 times in a row. Yeah?
How do you know it's not just responding to the input the same way every time? How do you know it's not just responding in the same way to the same input every time?
That's what it's doing, but we wouldn't normally think that a neuron would be capable of that, because what we're used to is neurons are very stochastic. Like, if you give it this input current, you should get a similar thing every time, but not the exact same, which is what's happening here. But they did this 25 trials in a row, and it gave almost the exact same response, like same spike timing to the very millisecond every single time. So this neuron is somehow remembering an input pattern and giving out the exact output pattern every single time. Yeah.
Can you explain the difference between the left and the right again?
So on the left one, they gave an artificial stimulus. So they just put an electrode in there and they cranked it up to like 10 volts and they just let it go for like 10 seconds. And what happened is that every time they did it, they would measure the output in terms of spike times. And so each dash is a spike. So as you can see, like, it's kind of similar, but it's all over the place. Every time it gave a kind of similar response, but not exactly. But it's kind of eerie that when they gave it this, in this case, they simulated a random current. So they gave it this same random looking thing every single time, which is more similar to what a neuron would naturally get. As you can see here, it gave the exact same output, like every time, except for a few little outliers.
So the input wasn't changed?
No, the input was the same every time. It was a randomly generated thing, so it was this crazy bumpy thing, but they gave it the same crazy bumpy input current every single time.
So the left one, they just kind of has like a really saturated input?
Yeah, like a tetanus, which is what we're used to giving, like when they generate LTP in a neuron. Okay. So that's another way that an individual neuron can remember information. And then this is kind of like, he was just giving an overview of like how neurons are stochastic. So as you can see, this is what we're used to. Every time you give it a little activity here, it'll give you a similar kind of spiky thing, but it's really pretty different every time if you look at it closely. So it's responding differently every time you get one. So that is the input, and these are all different output trials measuring the output voltage. And the theory that he proposed is that the stochasticness or randomness that we see in neurons is not like a biological accident. It somehow actually helps the brain compute information, or it's very useful. Like if it's survived to this extent, then it must somehow be useful to the brain in ways that we fully don't understand yet. So it's just like it's kind of a theory that they haven't proved. Okay, so moving on, there's 3 different types of computational learning theories that he discussed. unsupervised learning, which is where there's no teaching signal. So that's like a Cohen map where you just have it self-organizing itself. You let it go, it does some iterations, and it eventually outputs something, and it learns a certain direction that all the arrows point. Or supervised learning, where you have a teaching signal which corrects errors, which is the perceptron. It measures the error every iteration, and then it corrects a little closer to what the desired output is. So in this case, you have to give it what the answers should be, the desired output. And then finally, you have your reinforcement learning, which is the most like realistic, like real life type of learning. And this is about maximizing reward in a stochastic environment. We'll talk about it in a bit with an example with dopamine, similar to Dr. Shadmer's stuff. Also in this lecture 33, he went through all of like what LTP is and how it works again, so don't worry about that. You could look at either this or Kirkwood's stuff again to review that stuff. So we're not going to talk about it today. But how he went over an experimental example of how they implanted a false memory in a mouse's brain. And what they did here, they had the mouse in a room initially. So that's the first room. A is represented by a red triangle. And they had, I guess, electrodes in its hippocampus to measure its place cells. They found that these 3 cells were place cells for this particular room. And then when they moved the mouse to the room B, which is the gray square, they noticed that these gray place cells lit up. So the red place cells correspond to room A, the gray place cells correspond to room B. And then what they did though is that they shocked the mouse in room B, which is supposed to induce a fear response. So they gave it electric shock. And what they did at the same time, while they were delivering that electric shock in room B, they activated the place cells of room A in addition using a laser optogenetically. So what happened with that is so they were trying to implant a memory in the mouse that had been shocked in room A, even though it had actually been shocked in room B. And it worked. When they put it back in room A, it had a fear response as if it had remembered being shocked in there, and it acted afraid, even though it had only been shocked in room B, not in room A. And they saw those same place cells go off that they had stimulated before. So what they think they did is implanted a false memory in the mouse's hippocampus that it had been shocked in room A. Yep.
So now, if they put it in room B, will it also have a fear response?
It should have a fear response in room B as well, which makes sense. And then I guess probably for a control, they put it in a room C, where it had never been in before, and it had no fear response, I would assume. So yeah, any other questions about this?
Is that saying that in room A, the place cells for room B are now also being activated?
No, I think these are just gray to indicate which ones were originally room B. I think the stars represent stimulation. So in room A, these are stimulated. In room B, the gray ones are stimulated, but they also artificially stimulated red ones. And then when you put it back in room A, the red ones are again stimulated. But now I guess they measured the fear response probably just by visually examining the mouse.
So would the mouse also be afraid to be in room B?
Yes. It should be afraid in room B, which makes sense. That's sort of like the unconditioned response because you shocked it, so it should be afraid. In room A, there's no reason it should be afraid. It was never shocked. That's like the conditioned memory. Sort of like Pavlovian learning.
Do they do a control where they put it in a third room?
Well, I don't know for sure. Yeah, I don't remember like who did this study, but I'm sure if you look it up, you could find out the details. But this is all he mentioned in class. So moving on from that, this is an example of supervised learning, I guess. He didn't really describe it, but another example of supervised learning, you have a person throwing darts at a dartboard. In the beginning, they're pretty good. You put on these prism glasses, which are sort of like drunk goggles that make everything shift one way. And initially, they are really bad at throwing darts. If you let them do a bunch of practice trials, they can see the error, which is how far away they are from the bullseye, and then they adjust their movement. The next time they get a little closer, they still see some error, they adjust, and as they're getting better. So the learning signal in that case, similar to like a perceptron, is the distance from the bullseye that they see the dart go to. And they get better over time. But then if you take the prisms off, what's interesting is their normal vision actually is no longer trained. So now that even though they have the glasses off and they were good before without the glasses on, now they are bad again because their brain has learned the new method of throwing darts when having these drunk goggles on. So now they're really bad, and you have to give them a bunch of more trials and have them see the error and learn to supervise the learning signal. And this also is an example with Purkinje cells in Dr. Bastian's lecture, which he went into a lot of detail in. So if you want to learn that, you can go back to that. Another example, really similar, they had an owl, and they measured its visual and auditory receptive fields, and that's the white, the red V here and the purple A. So those are two receptive fields. Initially, they're on top of each other, which makes sense. That's what you'd want if you're an owl flying around trying to catch a rodent or something. You want to be able to hear it and see it at the same spot and coordinate your swoop in to attack it. But when they put these prisms on the owl to mess with its vision, initially when the prisms were added, the visual field shifted one direction. That makes sense because the prisms shift it, and the auditory field remained in the same spot. Makes sense. If you put these prisms on the owl, you wouldn't think it would affect its hearing at all. But what happened is actually after 8 weeks of training where they had it swooping down to pick up things, the auditory field had shifted over to join the visual field to the right of the original center. Because I guess the visual field of the owl's brain was acting as a learning signal to its auditory cortex and actually told its receptive field to shift over because that would make it better at catching mice again. That makes sense? Okay. And then the final thing we're going to talk about, just a few more slides, reinforcement learning model. So what's going on here, as we said, it's maximizing reward in a stochastic environment, which is like real life. And what happens here, it's actually really similar to Hebb's rule or the perceptron, where you have your weight, a sum of your weighted inputs, except that now, if you notice, it's continuous as a function of time, and your output y has changed to a reward r. That's the only difference, really. Conceptually, it's the same. The main difference is it's just continuous, and now output is reward instead of just like some abstract output. And it has the same gradient descent rule to get the error function right here, but now capital Y and lowercase y have been replaced with capital R and lowercase r as rewards. And the learning rule is still similar. You find the difference in reward, like the error of what you would expect the word to be versus what the actual reward is, and you multiply it by the input to get your new weights. And then an example of this is building off of what we talked about in Dr. Shadmer's portion of the class earlier. You have a monkey that it gets a visual cue, so a light blinks on, and it knows it's going to get some kind of snack like 30 seconds later. So that's what's going here. You have a conditioned stimulus, so the monkey's been taught to get excited when it sees this cue, even though the reward, which is the snack, actually comes 30 seconds later. So now these are dopamine cells, they're firing patterns. So as you notice, it doesn't go off when it actually gets the reward. It's been conditioned so that it goes off when it gets the cue. Because they believe that dopamine cells work using this reinforcement learning system, and they are actually responding to the difference in expected reward versus actual reward. So this is an unexpected moment where it knows it's going to get a reward, so the dopamine cells fire a lot. But in this case, the reward is expected, so big R minus little r is 0. So there's no firing here. But if you trick the monkey now, so that imagine if the trial immediately after this, they gave the monkey the cue, so it gets really excited, its dopamine cells go way up. And then 30 seconds later, you actually trick it and you don't give it the treat or snack. Then what's weird is that the dopamine cells, not only do they just not fire, they actually completely shut off. And there's this blank spot in their firing pattern. And these are across many different trials. So in this case, it would be like the expected reward minus the expected reward would be some large positive value. And the actual reward, which is lowercase r, would be 0. So there'd be a huge error signal, and that error signal is somehow making these dopamine cells go off. So that is evidence for the idea that dopamine cells work off of this reinforcement learning based system where they react to the difference in expected and actual rewards. Any last questions about this? Okay, awesome. I think that was the last slide. Yeah. I don't know how it's doing this. I'm trying to figure it out. Okay, all right.
Okay, so I'm going to talk about the last two lectures from Dr. Zhang's material. Okay, yeah, so that's mapping and population coding. So mapping in the brain, there are a few places in the brain where we have topographical maps, and what a topographical map is locally in the brain, areas of cortex serve the same similar purposes. So when we get into it later on, the motor homunculus areas that represent the hand are very close to each other locally, but globally, the areas that control your whole body can vary from position to position in cortex. And you have maps in 4 important maps: visual retinotopic maps, somatosensory, auditory, tonotopic maps, motor maps. And then I'll discuss this one computational model, the Cahonen self-organizing maps. So a lot of this stuff is going to be review from like Dr. Shadmir's lecture stuff too. So mapping in visual cortex. If this is what you see in your visual field, we have a certain representation of this in our cortex, and particularly superior colliculus. So this is your superior colliculus, and what this would look like if represented on your superior colliculus. Eccentricity in this case, which is this thing here, is the radius, or the radius, and A is the angle, so theta, relative to this horizontal line here. And you can see here, this is A equals -90, and this is A equals +90. The important thing to notice about the map of the superior colliculus is that fovea is overrepresented, and this is a common theme in most of the topographical maps in cortex. Areas that are important to us are overrepresented in cortex. So while fovea represents a very small portion of our field of vision, it's extremely important to us, and we have the highest visual acuity in that area. And this is, so this is what the map would look like if it was, this is what you would see, but this is how it's represented in visual cortex. And this is a conformal mapping transformation. I don't think it's something that you guys would need to know, but it's something involving complex analysis, and you make this transformation from here to here. And a conformal mapping preserves angles locally. So all the angles between these different lines here are going to be the same here. The advantage here is that you have this overrepresentation of areas closer to the center, or to the fovea in this case. And then here you have much bigger boxes out here, but here they're a little bit smaller than they are here. So you have that overrepresentation aspect here. And then orientation preference and ocular dominance maps are the other types of maps that you have visually. So orientation columns, so this is a colored map of neurons that preferentially respond to bars presented in specific directions. This is horizontal, and you can see all the other different directions. So this is approximately how the neurons respond according to their color. And then you also here have ocular dominance columns, where black represents left eye dominant and white represents right eye dominant. And this is an overlay of the two maps. And you can see here, like locally, orientations are all very similar, and like locally here too, but globally you have both left and right eye represented, and here globally you have all of the orientations accounted for. And yeah, here's the overlay of both, and here's a singularity. I'm not really sure what the relevance of that was, but there it is. So mapping in somatosensory cortex. So this you guys have seen a bunch of times. This is a motor homunculus. It's a visual representation of how much area of cortex we have devoted to each of these components. So our arms, our fingers are obviously the most important, and our hand is really important because that's our primary method of interacting with the outside world, like Luke said. And you can see here, this is how it's represented in cortex. And locally, we have a lot of similar representations here. But globally, we have representation of the entire body. And here's another interesting thing for rats. Their whiskers are their primary mode of interaction with the external environment. And here in cortex, you can see each one of these little circles, I'm not sure if you guys can see them, represent control of one single whisker. So that's kind of interesting to see in other things too. Mapping an auditory cortex. So the example here is a bat. And the important thing to notice here is that this is the area of cortex. So this is just an enlarged picture of the brain here, of the bat's brain. And this is how it responds to auditory stimuli. And here you could see that it's arranged by frequency with, I think, the highest frequencies here and the lowest frequencies here. And certain very important frequencies, this is around like 60 kilohertz, take up a lot of space here. So this is another example of how echo sounds, or in this case, echo sounds that are important to the bat, have a very large representation in cortex, because this is likely the type of sound that the bat generates or that they get back from their prey when they're trying to hunt and things like that. So these serve very important biological purposes. And motor mapping. So again, this is the superior colliculus, and here on the left side, you have these lines, and for each line, it represents what happens. It represents what direction and how much your eye would saccade if stimulated in that specific location. So if I stimulated your eye up here, it would make a really, really tiny saccade up and to the right. But if I stimulated your eye down here, it would make a huge saccade down to the right. And this gives us an idea of how we represent our visual space, because that means down here, it represents something a lot farther away from the center of your field of vision. So you get an idea of that, and based on stimulating the superior colliculus in various locations and determining how far and where you saccade to, you can get an idea of how the superior colliculus is mapped with respect to angles and distances and things like that. Are there any questions about this so far? Yeah?
So is the idea here, if you're far from the fovea, then the movement has to be bigger? Is that what you were saying?
Yeah, so here, like, right here is like -40 and +40, so that's pretty far from the fovea. So the movement in order to get there has to be a lot bigger. So that's just the length of that line. Yeah.
So is that the only thing we can get from this slide? I can't think of any sort of question.
Yeah, that's pretty much it. For mapping, the primary things that you guys would probably need to know is just that there are maps that exist, and they represent, yeah, exactly. These are examples, and they represent important areas of cortex, or important areas.
Would they ask us like what examples of things, or is it more like, because that's really
yeah, if you were to get a question, probably something like that. Like, give me an example of somewhere in the cortex where you have a map, a topographical map of something. And these are some counterexamples. So not everything is mapped in cortex. You don't have so in mouse visual cortex, they don't have a map of orientation columns, and you don't have a map of preferred direction for head direction cells or map of place fields for place cells. And what this means is that, like Antonio said, you can't have all your place cells representing every single possible room or location in the world, and it's all relative to landmarks. So while your place cells may respond preferentially to specific locations in a given room, those same place cells might respond to different locations in different rooms or different areas. It's not some fixed representation of a place or head direction. It's relative to where you are. And locally might not have the same, so for example, head direction cells, locally they might not have the same head direction, and that might change from location to location. Are there any questions about that? Okay. And now I'll talk about the Kohonen self-organizing map. So this is pretty important. So I have some definitions on the left here. Let's assume that we have neuronal units on a two-dimensional grid. So this just means if you think about a coordinate system, X and Y, and each spot is one neuron, and you can make it arbitrarily large. So the definitions, so WR is the preferred direction of a neuron at location R. And this you can think about as the weight of a given neuron. And the preferred direction just means that it responds most to an input that is most similar to that direction. X is the input to all neurons. It could represent a reach direction or something like that, but in general, it's some direction that is given to all of the neurons, and you'll see why that becomes important when I talk about the updating and things like that. Y is the response of the neuron at location R to the input, and R star is the location of the neuron with the highest response. And sigma, which is in this neighborhood function down here, represents the width of the neighborhood. The higher the sigma, the more neurons get updated. Lower sigma, fewer neurons get updated. So here we have the response of a given neuron at location R is represented by the dot product between its preferred direction and the input direction given to that neuron. So that the dot product just gives you pretty much how far apart two neurons are, or two vectors are by their angle. And the input X is the same for all neurons, and it can represent a reach direction or something like that. And this weight vector varies from neuron to neuron. So you don't want all your neurons having the same preferred direction, because then you're not encoding any information really. So your learning rule, so in order to update your weights, you use the neighborhood function. So the distance between your neuron that you're interested in and the neuron with the max response times the difference between your input direction and the direction of the current neuron that you're interested in. And this is the neighborhood function. It's kind of like a Gaussian. And like I said here, sigma represents the width of this neighborhood. If your sigma is really big, you'll update a lot of neurons. And I think you guys saw this on your homework assignment. And when you make sigma really small, you get this completely disorganized map, and nothing really gets updated. And this describes how activity falls off from the maximum location. And I guess that's pretty much it on that. Are there any questions about this? Yeah.
What are we going to do with this?
I think it would be important to understand the concepts, definitely, and like the effect of sigma,
Right.
what this weight up.
Like it's cool to see this, but we're going to have to use that and how, because that would be important tonight.
Like on the exam, are you going to have to use it and things like that? I think you'll just need to conceptually understand it. Yeah, like know things like what I described here, like sigma and stuff like that. Did someone else have a question? No? Okay. So this is important stuff. And self-organization can help explain neuroplasticity. And here, this is an example of a monkey's hand where the second digit is stimulated up here. And this is the representation of a normal monkey for that given receptive field. And this is post-stimulation. And self-organization, so what happens is when a neuron has the highest activity, it also activates and updates the neurons around it. So in this case, if we apply that to this example, if we have an area of cortex up here where a bunch of neurons are activated a lot, it'll also activate the neurons around it. And this is one potential model to explain why we have neuroplasticity in the brain. Is there any questions at all on that first lecture? Yeah.
Can you go back to the neuroplasticity part?
Yeah. This one?
So can you, so how does this explain neuroplasticity?
So if I have that up there for a normal monkey that isn't stimulated their second digit all the time, they have this size of cortex. But if I stimulate it a lot, then these neurons activate the neurons around it. So when you have a self-organizing map, you have a neuron, and neurons around that neuron get updated because of that highest activity of that neuron. So if you think about it like this, each of those neurons has like a little neighborhood around it of neurons that it affects. And with enough stimulation and with enough time, those areas of cortex will take over other areas of cortex.
What if you, let me see, I guess what if you just lose a part of your, let's say a part of your, I forgot what slide this was, but it was a part of your part of your brain just goes blank, right? How will I guess the neurons around that area that goes dead, kind of organize itself, I guess kind of take over that the region that just went dead.
So you're saying how does that happen?
Because it seems like you can't reach, if there's an area, right, where we're if you're comatose, right? You're like
Right.
not using your like motor cells, like your like motor cells at all.
Right.
So it seems like in order to like, it seems like there's like I think my question is too complex.
If you want, you can ask after the review session. Okay. Oh, sorry. Did you have a question?
Yeah.
Yeah.
Go to the previous slide again.
Oh,
so
sorry,
when
that
you
one.
try to apply stimulation for the second digit,
Right.
is that going to affect the third and the first because they are adjacent neurons, or this is going to affect only the area that is not related with this?
So that I'm not sure, and I'm sure there are factors that will take over maybe other areas of cortex like digit 3 and digit.
Yeah, because it's very straight, as you can see, the area of 3 and
Right.
and after. So
Right. Yeah, I think there's other things at play, and like I think Dr. Shadmir had in his lecture, there's like this inhibitory interneuron in areas that are neighboring areas of cortex. So there's also that factor at play too. So I'll move on to population coding. So we can do very, very fine motor tasks, even though most of our motor neurons have really broad tuning curves like this, which represent a wide variety of degrees. So how is it possible that we can make movements more precise than our least precise neurons, if that makes sense? So yeah, imprecise neurons can encode precise data. And how is that possible? So here is an example of a monkey's receptive field mapped on their hand. And you could see that all the receptive fields are kind of overlapping here and a bunch of other areas. But in each individual receptive field is pretty big. And the monkey can actually discriminate two-point discrimination at a much smaller than these individual receptive fields. And a lot of it has to do with the fact that these receptive fields are overlapping and they carry more information that way. And color also, in a similar way, involves relative activity of different cones. In the same way that if I touched a specific point on a monkey's finger, many different receptive fields would get activated. So in the top, we have a bunch of broad receptive fields. So the whole population carries more information. So for a given stimulus at any point along this axis, we would activate way more neurons if we had a bunch of neurons with broad receptive fields than neurons with narrow receptive fields. However, in this case, each individual neuron carries more information. And the key takeaway here is that a broad receptive field is not always bad, and most of the time is actually better. Yeah, did you have a question?
Yeah, it just, in both examples, it's like very uniform. They're all broad or they're all narrow. Is that
Right.
how it is?
No. So so like even here, in this monkey, you could see that not all of these are all the same size, right? Some are more broad than others, but the overlap allows you to get more information this way. And that's the key important thing about the broad tuning curve. So you can get more information even though the size of the receptive field is larger. With that more information, you can perform computation and determine, you can get information that's more specific than the size of the receptive field. And this is math involving the population vector. So if you have a reaching direction given by a vector r and angle theta, the firing rate above baseline for a neuron I, and this is a model. This is how we're assuming the model, the neuron has its activity. So its activity is equal to the dot product between pi, which is the neuron's preferred direction, and r, which is the reaching direction. And this is really similar to the Kohonen math. So the highest response neuron was the dot product between the preferred direction of that neuron and the input to that neuron. So this is pretty much the exact same thing. The population vector overall is defined by a weighted sum of the activities times the preferred direction. So using this as an example, so here we have a monkey that was told to make a bunch of different reaching directions, like along these large black lines. The tiny black lines here represent the activity of a bunch of different neurons along their preferred direction. The longer the line here, the higher the activity that it has. And using this population vector, this red arrow is what you get and what you recover back using this. And you could see that this population vector pretty closely matches the reach direction a lot of the time. And this is pretty important and very useful, especially if you're trying to move a prosthetic arm using population vector recording from large populations of neurons and things like that. Does anyone have any questions about this? Okay. So the principle of the population vector and why you might be able to do math like that I did on the previous slide. So population vector always recovers the reaching direction if this holds true. If the sum of the population of the preferred direction times its transpose equals the identity, where I is the identity, preferred direction. This is because, so from the previous slide, we know that that the population vector is a sum of the preferred direction weighted by its activity. And if you replace the activity with the formula from the previous slide, which is pi dot r, you get this, the dot product of two vectors is the same as the transpose of the first vector times the second vector, since these are both column vectors. And then rearranging this, or not rearranging, using like the associative property, you just put the parentheses around these first two things, and you can see that if this is identity, v equals identity times r, which is just v equals r. And a special case that satisfies this condition is a population of uniformly distributed preferred directions, which is roughly true in the motor cortex, which is why roughly this red line corresponds with the big black line of the reaching direction. Are there any questions about this? This slide is important too. Yeah?
What were the individual black lines in the previous slide?
Each individual one here.
Yeah.
It's the activity of a neuron that has that preferred direction. So this black line would be a neuron with that preferred direction and that activity. The longer the line, the more activity. Any other questions? Okay, I think this is all I have. So, yeah. Yeah, that's good.
Okay, so I'm going to cover the two guest lectures by Dr. Vogelstein and Dr. Sarma. Dr. Vogelstein went over what he does in statistical connectomics and some basics to help you understand what the field is all about. And Dr. Sarma talks about deep brain stimulation and how that works and why it works. So first, some graph theory basics. So start off with a graph is defined with a set of vertices and a set of edges, where the edges are subsets of the vertices defining the relationship between like any two vertices. And importantly for what Dr. Vogelstein was talking about, we're talking about random graphs, which are basically your graph is defined with a probability distribution. So you have a function that tells you how likely it is that there are certain connections or certain patterns in your graph. And it's the whole graph and the connections within, that's the random probability distributed part and not the vertices or edges themselves. So we use this a lot. It's the adjacency matrix representation, where you're going to have rows and columns that are nodes and your values are edges, which we can, they're useful when you talk about, oops, there we go, simple graphs. So we like to focus on simple graphs because they're basic, so the properties of a simple graph is that they are undirected, no self-loops, and no multiple edges or like edge weights. So this would be a simple graph, and everything else here is not. So, and in the matrix representation, like you could see before, those were all simple because they're all binary number values. And there are no self-loops because you can see that the diagonals are all 0. Yeah. So with these basics, you can then talk about models such as the Erdős-Rényi model to represent, say, your brain, which is what we're interested in. So with the Erdős-Rényi model, you can use a single parameter, that is a probability value, to tell you how likely it is that there's a connection between any two nodes, an edge between any two nodes. So with this model, you have the single parameter, and each edge is independent from every other edge, and that if there is one edge that exists, the edge next to it doesn't care. And they all have the same probability of existing. So using such a model, which is the only model that he talked about, you can do cool or useful computations and experiments, say with some phenotype. It could be a disease, a psychiatric disorder. So you will have one variable that defines what the graph of your patient's brain is, and one variable that defines whether or not you have some phenotype. Technically, it doesn't even have to be binary. You could have various phenotypes that could be defined. Anyway, so with these two variables, you can then have a joint probability. So you want to know whether the graph that represents a patient's brain is that graph because they have some phenotype or not, because they have some disease or not. So you want to see, so the hypothesis test would be that, say, the example that he used in class was if you have bipolar disorder, is the graph of your brain going to be different than somebody who, or significantly different than somebody who doesn't have bipolar disorder? Does that make sense? Yeah.
I'm confused by what joint probability means.
So
over that again?
Yeah, so joint probability, or this one, is the probability that you have some x and some y at the same time. So here it would be having the probability of a specific x graph as well as y being, say, 1. So that's why you can also say it at the same time as f of x given y times f of y, because f of y is the probability that you have y equals some value, and depending on that value you have f of x, so it's the probability that the two are occurring at the same time.
Okay. Cool.
I think that makes sense. Any other questions? So with the hypothesis test, then you can actually compute the values that you want. And with the simple graph that we're using, you can simply add up all the values in your adjacency matrix, that's binary anyway, and divide it by, so you want to average a matrix, so you divide it by n squared, which is the number of possible edges, and that gives you a probability of there being an edge at any anywhere that there can be an edge. So you do this for all your patients and average that to get this one parameter that you can compare between patients that have the phenotype and patients that don't. So you will have an average of patients with the phenotype, average of patients that don't. Compare those. If they're the same, then you can accept your null hypothesis. If they're different, you can reject them. So this is a simple example of how you can, modeling the brain using these random graphs can help you study or get data about what differences there are in different people's brains. And yeah, so we also want to, but simple graphs aren't going to encapsulate everything that the brain does. So we want to know that in the real brain, they're not going to be, connections aren't going to be identical. You want to look for, so you're not just looking for individual connections. You want to look for, say, triangles or squares, i.e. cycles, of where one edge, one connection that's there is going to affect the fact that there's another connection to another node, and such patterns is going to affect how your brain works. So these are interesting things to look for. Yeah.
Can we go back a slide?
Yeah.
So basically, are you just like comparing the distribution of like the number of edges?
Distribution.
Like the random variable, right? That you're like, for each patient, right? I guess. Let's say for everyone who doesn't have bipolar disease, right? You're basically taking the connectome and you're just adding up all of the edges.
Yeah.
Right.
Yeah.
And basically, you're seeing if like, so after like, if you have like 10,000 patients for like someone who's like, let's say there's like 10,000 patients, right? For people who are like normal and who have bipolar disease, right? So for each population, right? Basically sum up all of the edges, right? For each connectome, right? And you just look at the distribution of the total number of edges in the graph. And you're trying to see if like, oh, if they're like, if like you can use like a t-test to like see if they're statistically different.
Yep.
Okay. Just to make sure.
It wouldn't like necessarily go to the equal, like they're close enough such that it's
yeah.
Okay.
Yeah. So statistically equal or whatever.
Question.
Yeah.
Wait. So like, can you go to the next slide? Oh yeah. So like, this is like, why did Augustine choose the sum of total number of?
It's just an easy way to get a single parameter because it's an Erdos-Renyi, so you're going to have like the one parameter, which is the probability. So if you sum them all, divide by the all the possibilities, you're going to get an average, which is probability, which is a single parameter in the Erdos-Renyi model.
The maximum like the estimates?
The
maximum like the estimate of the P?
Yeah, that's one way you could do it. Yeah. So anything that you like learn from PropStat, statistical tests, you can apply to this. But like this was just like the most basic example you could give for this type of work.
I think it's like it's assuming every connectome is like our Erdos-Renyi graph, right? And you get and basically the only parameter you tune in the Erdos-Renyi graph is the probability of an edge occurring, right? Yeah. So this is like seeing like, oh, can we detect difference if we change like a different if we change the P for like the Bernoulli.
Bernoulli?
that one? It's like, yeah.
Yeah, so I mean, the point of this slide is that you're not going to end up using Erdos-Renyi for your models when you start thinking about the real brain and how complex it is. But the Erdos-Renyi is a good starting point. So yeah, so a lot of connections are unknown. So instead of like modeling and looking for something very specific, you want to just find like types of connections, or like what they call graph properties, that could be more prevalent in your patients with the phenotype, say like with bipolar. And so that way you can, instead of just knowing what you're looking for, you want to identify these properties that could be important to use in like a clinical perspective. So with a tractable model and like an efficient way of like finding such properties, that could be cycles, could be any kind of pattern, you're going to be able to find these properties that define disorders, hopefully. That could be used as a kind of like symptom or marker. Yeah. So, any questions about graphs and connectomics? So then Dr. Sarma talked about deep brain stimulation and how it's used for Parkinson's disease and why it works, most interestingly. So first, we've talked about Parkinson's both with Shanmir and with Bastian before, but Sarma talks about how in Parkinson's, 80% of your, or more, of your substantia nigra pars compacta is damaged, or essentially the neurons are dead. So various treatments that can be used include lesioning, so like completely removing like the parts or whole of parts of the basal ganglia. You could medicate, but that only works up to a certain point until your patient builds up tolerance. So after 10, 20 years, your medication might not work anymore. And then finally, deep brain stimulation, which seems to work really well. And she showed that example where it's like a drastic improvement when you turn the stimulation on and off. So background on like how they decided to model Parkinson's disease and study deep brain stimulation is they looked at how the basal ganglia essentially gives a signal for selective motor processing. So you have this basically control system where your primary motor cortex gives a movement, and that feeds back to the sensory motor cortex, and computation and analysis is dealt with in the thalamus, and your basal ganglia modulates as needed based on what you want to do and any other information it has. So in Parkinson's, you have this whole circuit is hampered because you have excessive or just unnatural oscillations and synchronization in parts of this circuit. So specifically in your STN and GPI, which is part of your basal ganglia, and just your cortex, various parts of your cortex. So this would affect your U of T, since that's coming out from your basal ganglia, and your V of t from the cortex. So with those, with irregular U of t and V of t, your control circuit breaks and your movement is affected, which leads to all your Parkinson's symptoms. And the treatments that seem to work is lesioning, which removes the basal ganglia, so you just don't have a U of t, and so you don't have like an irregular feedback into your thalamus that would break the circuit. Or high frequency DBS, which appears to regularize U of t, and the next few slides is like why it seems to do that, why we believe it does that. So the same graph, but highlighting the fact that the thalamus acts as a relay because your basal ganglia is giving out these signals, and your thalamus is the computation part that signifies how much of your sensory motors and how much of your like intents is going to translate into a different movement. So PD patients seem to always have this relay switch as open, in that like nothing seems to be getting to the primary motor cortex in terms of feedback. So and the frequency selectivity of signal U of t affects the relay. So that's talking about how when your signal from U of t is fast, it seems that that thalamus relay is going to be okay and relay your information properly, and when it's slow, it doesn't. So that goes into why we think, partly why we think DBS works, since a reliable frequency for DBS seems to be about 130 hertz, which is a really high frequency and actually nowhere near close to what it naturally is in a healthy patient. But it works partly because it gives this fast U of t to the thalamus that can restore the relay. But that's not all, since if that was the case, then any high frequency would work, and 130 hertz seems to be the key. So,
wait, can you go back?
Yeah.
Sorry. Wait, what does fast and slow mean?
So, like fast frequency, slow frequency. Yeah? Any other questions? So this is the most interesting part of the deep brain stimulation. Because, so usually your signals in your brain go in one direction, like through one pathway, as like a normal pathway. But when you stimulate your brain artificially, it goes both in like that normal forward direction and to a backwards called antidromic direction. So this is important here because you then get this forward pathway that goes through your GPI, thalamus, motor cortex to the striatum, as well as a backwards pathway from the STN through the GPE to the striatum. And because of this 130 hertz and like the period that it translates to, these two, the signal from the forward pathway and the backwards pathway are going to coincide in your striatum, causing this resonance that leads to like a regular signal from the striatum and all its downstream and any downstream parts of this control circuit, so that your signals from then on are regularized and not that irregular pathological signal that you would see in Parkinson's disease. So so from the striatum, it goes back and restores a more normal activity in the thalamus, which repairs that relay switch and allows for Parkinson's disease to have patients to have like normal feedback circuit to control their motor movements. Does that make sense? Oh, is that it? Because that was my last slide. So, yeah. Any more? I got more.
Almost done, y'all. Okay. So thanks for sticking around. Sorry it's taken a while, but I'm going to give you a few highlights from my lecture.
You know exactly what's going to be on this.
I don't know. Okay.
Come on.
Okay, good point. So if I were you, I would read this definition, know what a brain-machine interface is, and know that this definition is not something that's set in stone. As technology evolves, this definition changes. Know the major components of a brain-machine interface. Know that you need to extract some signal from your brain, do something with that signal, and then have it issue some command to some end effector. Know how you get different signals. So know that an EEG electrode will give you an EEG signal and more or less like the frequency components of that signal. And then know that brain surface electrodes give you an ECOG, which give you a different type of signal, things like that. And then also keep in mind where you place those electrodes. They can do different things. So something that you place in the motor cortex will let you record motor signals, intended movements. So then you can use that to move a robotic arm or something. And then you could also stimulate in the somatosensory cortex to elicit some type of sensation. So where you put these electrodes is important. So that's BMI stuff. And then there's this other idea called pattern recognition, which is slightly different. It's something separate than a BMI, but it's a surgical procedure where you can take an existing muscle, cut it up into different pieces, and put nerves that have been amputated into this muscle so that the nerves can regenerate and grow. And then you can control what would have been your forearm, say, by contracting a particular part of that muscle that has undergone TMR surgery. So the idea is that these muscles now act as a biological amplifier for the control signals that are generated from your nerves. And this is an example of how you might use this. Let's say you place electrodes on some part of your body and you perform some contraction pattern. If you did the lab, you did something similar where you make different movements with your hand, and what you're doing is you're capturing that EMG signal, that muscle activity, and then you can classify it with some algorithm. So what y'all used in lab was called linear discriminant analysis, LDA. And essentially you can use that to separate your EMG activity into different groups and use that to identify different hand positions, whether it's a point, hand open, hand closed. And then you can use that information to control a prosthetic limb or manipulate a training environment like you did in the lab. Basically the idea is you create these classes so that next time you see an EMG pattern that fits into one of these classes, you know that it's a particular pattern. And that is all. Yes?
Sorry, what does the L in LDA stand
Linear. Yep. Any
DNA stand for?
discriminant analysis, I think. All right, that is all. Thanks for sticking around.